Hello everyone and welcome to another video about acquisition of electrophysiological signals. My name is Marija Novicic and in this exercise I'll show you how to make a Labio program for fatigue detection using electromyography signals. In previous videos we showed you how to make a basic data acquisition application. We're going to start from that application so we can talk a little about the parameters we have to select. So, we already discussed it and said that the RSE means that we are measuring signal relative to the ground. That is the case in this exercise also, so we're going to leave that as RSE. Also, we're going to collect samples all the time the program is running, so we're going to select continuous samples option as a sample mode. Okay, so all of these controls we have to set to the correct values, so the program and the acquisition of electromyography signals will be correct. Sample rate has to fulfill this one condition. That is that it has to be at least 2 times bigger than the maximum frequency of the frequential spectrum of the signal. So the EMG signals is most likely to go up to 500 Hz, so we're going to set the sample rate to 1000. Next, we need to choose from which device we are collecting data. We're going to choose device 1 analog input null because that is where our output of the EMG amplifier is connected. Minimum maximum values are going to stay the same, so 5 and -5 volts. And we have to change the number of samples per channel. Number of samples per channel tells us how much samples we want to have at one scan. So I'm going to set this control to 500, so we can have in one scan of while loop 500 samples. In that way we can easier calculate some parameters and in the end detect fatigue of the muscle. Okay, so waveform chart will be our indicator for our EMG signals. So I'm going to name that as EMG data. And this will be amplitude of the signals, and this will be the time. Okay, so let's go to the block diagram. I'm gonna widen this up so we can fit our code here. In this exercise, we're going to use biomedical toolkit that has some functions that we can use for filtering the electrophysiological data and calculating some important parameters. So in the function palette, I'm going to go to biomedical toolkit palette and I'm going to pin it to my block diagram. Okay, so this palette works with waveform type of data. So we're not going to collect the array data as an array. We are going to use the waveform type. So we're going to analog, simple, single channel, multiple samples, waveform type. And immediately our indicator changes its colors to signal as it is the waveform type. Okay, so first, because we are measuring the signals that are low amplitude, they are easily affected by the noise, like power supply noise. So that is the noise at the frequency of 50 Hz, and we want to eliminate that signal. So we're going to use a filter that is in biosignal measurements folder under pre-processing folder, and we are going to place it at the block diagram. So this block gives us a lot of possibility. We can use classical filtering, but we also can use notch or comb filter. We are going to work with waveform data, so we are going to select that and connect our biosignal, in this case EMG, with the data from the output. Next thing we have to set is this error, so we know if some error is produced here, it will affect this block, it will not execute, and the program will report an error. Okay. Next thing to do is connect the important part of this block, that is the frequency we want to eliminate. So I'm going to go right click and create constant, and the default value is 0.1 Hertz, but in Serbia the power noise is at 50 Hertz, so we're going to set this to 50. This input DF is the bandwidth around this 50 Hertz that we are going to eliminate. So the default value is 0.02, but that is too narrow for us, and we can easily set this to 0.2. Okay, so now we are going to eliminate the frequency band from 49.8 Hertz to 50.2 Hertz, so 0.4 Hertz. But our most important thing to eliminate is this noise at 50 Hertz. Okay, so we can specify here that do we want this filter to be notch or comb? The only difference is that the comb filter eliminates the noise from the 50 Hertz and all the multipliers of that frequency, and notch eliminates only this frequency. So we are going to choose notch, so not comb filter. Okay. How are we going to detect if there is a muscle fatigue happening? We need to see the position of median frequency in our spectrum. So that's a frequency that divides our frequency spectrum of the signal into two equal parts. By equal, I mean they have the same area. Okay, so this toolkit has a block that gives us that information. It's under EMG and then median power frequency. When I place it on the block diagram, we can see that it has a lot of inputs and outputs. So what input we need to connect is, of course, that EMG data input. So we're going to connect it with output of the filtering block. And as the output, we get the spectrogram that is time frequency spectrum analysis. One axis of that chart is time, the other is frequency, and it has different colors that specifies the amplitude of the signal. But in this case, we don't need that, so we're not going to use that output. We're going to use this output called MDF, that is median detected frequency, and it is saved in this case as a cluster. That cluster has some fields, that is T0, started point of the time, dt or delta time, that is 1 divided by the rate, and the median frequencies. So why are we having the array of median frequencies? Because we get the frequency for each time being in our spectrogram. We don't want to work with that. We are going to work with only one frequency. But before we even get this frequency, we need to connect all the other outputs of this block, inputs of this block. So first I'm going to connect the error out and error in input, a terminal. And now we have these two inputs. First is time frequency sampling info. I'm going to create one constant. Okay, so what does this mean? This is the time, this is the window on which he is going to calculate the spectrogram features. So this is frequency, number of bins, and time number of bins. In other words, that is a resolution of our frequency and time axis in our spectrogram. So because we only have 500 numbers of samples in one iteration of the loop, we are going to set this at 256 bins. And for time, we can set it to 200 bins and be happy with it, how it will calculate the median frequency. Next input is window info. That is the info for a type of the window that he is going to calculate the spectrogram features. And the default value is Henning window. That is good type of the window, so we are going to leave that as it is. I'm going to double click it so it takes up a less area of our block diagram. So let's get back to this median dividing frequency. So I already told you that this is a cluster with 3 parameters, so we need to get only one, that is a frequency. We are going to use unbundled by name block from clusters class invariant folder. I'm going to put it on the block diagram and connect it with our output cluster. Instead of T0, I'm going to choose frequency. And now we have an array at the end. Let's see if that it really is the array. I'm going to create an indicator and see what we have. Yes, it's indeed an array. Okay, but as I said, we don't need that array. We need only one element, and we are going to calculate it as a mean value of all of these frequencies. So we are going to get the whole spectrogram, the all 200 time bins with all 200 frequencies that are median, and we are going to calculate mean of that. So we are going to use mean function, put it in the block diagram and connect it. Okay, so another problem we can get is that this output here, the frequencies are very noisy. Well, not noisy, but it isn't a smooth characteristic. It's very, has some peaks and it goes up and down fast. So the good thing to do is to take a median filter on that values and spoon the function. So we're going to use function that is called median, but point-to-point median. And what does this block do? He takes the input value, that is only one number, and he calculates the mean on that. But not only on that value, this block waits some samples to arrive and then calculate the mean value of those samples. How many samples we are going to wait is specified on this terminal that is called sample length, and we are going to say that 50 samples is enough for us to calculate the median frequency, so that characteristic is smooth. And finally, at the end, we get this median frequency, so I'm going to place one indicator calling FM, like frequency medium, and that is it. Okay, so the last thing I'm going to do is to connect this error with this stop button here, because if this block produces an error, we want to stop the execution of this V. So I'm going to replace this with a compound block with an OR circuit. And because this is a cluster, I'm going to need only a status part of that cluster. So I'm going to use unbundled by name again, connect it to our error, and this status of error connect to OR circuit. Okay, so that is our main part of the application. I'm going to do this now. And I want to do another thing. That is, I'm going to delete this because we don't need that, and immediately this broken wire on our block diagram. Another thing I want to do is to not represent this median frequency as only numeric indicator, but as a graphic indicator, so we can see its change during the time. Because fatigue of muscles is detected when the median frequency starts to fall. So I'm going to replace this with a waveform graph, and I'm going to wind this up so we can see it like that. This is time and this is FM in Hertz. And the units for this are volts, of course. Okay, the final thing I'm going to do is to make a sequence so we can initialize all these parameters that we are using. As we're going to clear the graph and we're going to make this stop button false at the beginning. So I'm going to place a sequence structure before this while loop, but to collect these initialization parts. So in this sequence structure, we're going to place a property node of this EMG data indicator, and we're going to use history data. And if we set the constant that is equal to default values, in the beginning of the program is going to clear the chart. We're going to do that also for frequency median indicator. Change to right. Okay, so the difference between these two is that this is a waveform data indicator and this is the double array data indicator. Okay, so our stop button has mechanical actions latch when released, so we actually don't need to put anything on the initialization because it will always go back to a false value. Okay, that is it for this example. See you next time in another example.
The previous video presented code programming for the application that could be used for real-time muscle fatigue monitoring. An example of electromyogram EMG is shown in the figure top left. The decreased amplitude in case of fatigue muscle could be observed. Fatigue detection could be also observed in frequency domain in the figure bottom left. Median frequency of EMG power spectral density decreases in case of muscle fatigue. Right figure presents the bipolar configuration setup for electrodes for EMG recording in our demonstration. We have used a homemade EMG amplifier and USB 6008 for data acquisition. 1 kilo weight was used to induce muscle fatigue. This video demonstrates the real-time muscle fatigue monitoring of the subject. Left graphic shows notch-filtered EMG signal. The right graphic shows the estimated median frequency. You can see here at the end that the median frequency decreased because of muscle fatigue.